All right, hi there. Happy Parent Teacher Conferences Day. I wanted to make sure that we got a class in today because we have a test coming up and we want to make sure that we can review as soon as we get back. So the announcement that you can see from Google Classroom, which is probably where you should be in your other tab, is we're going to look at the 12-2 mock test. You can already see that on the screen. You'll pause in a minute and mark it and submit it. Then we'll go into topic 7.3. Topic 7.3 is the last of the new material that we're going to look at, and it looks at the most modern physics that we will study in this course. It looks at what's known as the standard model of matter, which is a particle model of all of the forces and all of the matter that exists in the universe that we know of. So it pretty much covers everything. It seeks to describe the strong force, the weak force, and the electromagnetic interactions of all known particles, and it's really the crowning achievement of 20th century physics. It is the most complete description of matter that we have. It is not something that you will have a strong working knowledge of after today, but it will be something that you will see have a little familiarity with. Just looking ahead, we have our topic 12 test on Friday, so that's the 15th. And next class, we will have the bulk of the time to review questions that you have from topic 12, and also to practice some of these topic 7.3 skills and answer questions there. The topic 7.3 mock test is going to be due right after March break, and that's when we'll go into our review of like your mock tests and stuff like that. So there's a couple of slide decks here that we'll look at in a minute. It's probably a good idea to pause right now, take out the work that you've done on your 12-2 mock test, and go ahead and mark that. And while you do that, I'm going to pull open the 12-2 mock test, and we can go over the various questions. I'll try to explain those answers to you. So let me split this side by side. And oops, wrong one. Okay. There we go. Hopefully you've marked it already. I'm going to just quickly talk through the questions that are probably most challenging. The Rutherford-Geiger-Marsden experiment, that's the one that identified the nucleus. And it had most of the alpha particles were undeflected because most of them don't hit nuclei. When we look at question 2, let me make this just a little bit bigger so that I know it shows up on your screen. I can probably move this over to the side now. So when we look at alpha particles scattered at the nucleus, small deviations from the predictions of the Rutherford scattering model are observed, which change in E and Z are most likely to result in greater deviations. We know that that deviation has to do with alpha particles being absorbed by the nucleus, so they go missing. That's going to happen when you have your largest energy alpha particles, and it's going to happen when you have your largest radius. It's going to happen when you have your smaller charge nuclei. So that these alpha particles will be able to penetrate the furthest in. So that's why it's B. 3. The diameter of a nucleus of a particular nucleotide X is 12 femtometers, 12 times 10 to the minus 12. What's the nucleon number? We know that this is related to the equation. The radius is equal to 1.2 femtometers times the mass number raised to the 1/3. So this is 10 times 1.2. So the number that raised to the 1/3 gives us 10 would be what to the 1/3 gives us 10? It's going to have to be, well, maybe it's not 1.2 femtometers. 125 would give us 5. Oh, because it's asking about the diameter. Okay, so the diameter is not the radius. So we go, it's 6 is the radius. That's 5 times the 1.2. So to get the value of 5 for the multiplier, we have 125 to the 1/3. 4 says the diameter of the silver nucleus is approximately 3 times that of the diameter of which nucleus? So in this case, we have 108 total particles. And we know that the radius scales as the 1/3 power. So if we want the radius to be 3 times as large, we need it to be 27 times as many particles. 27 times what number gives us 108? That would be approximately 4. So we're looking at helium here. A pure sample of radioactive nucleotide N0 at time 0. At time t, there are N atoms remaining in the sample. The half-life is t to the 1/2. What is the decay rate of the sample proportional to? The decay rate is always going to be proportional to the number of particles existing at that moment. So that's going to be N, whatever the number is at any moment. Samples of different radioactive nuclei have different numbers of nuclei. Which graph shows the relationship between the half-life and the activity for the samples? So larger values for the half-life will show smaller activity. Those values are related by an exponential relationship. So e to the minus t. I guess it's no, it would be 1/2 raised to the time divided by the half-life. Give times the number of particles is gives you the activity. Which one would we be looking at here? D shows an increase in activity leads to a decrease in half-life. There we go. So it's that inverse natural log. It doesn't actually go to 0. Next one, we have the half-life is 8 seconds. The initial activity is 10,000 becquerel. What's the activity after 4 seconds? So 4 seconds would be less than a half-life. So we're definitely not going to cut this value in half yet. So we're looking at either C or D. The way we would do that is we would look at the number 1/2 raised to the 1/2, or the square root of 1/2, which is going to be 0.717. So it's going to be C. 8, the graph shows the variation in the natural log of activity versus the time for a radioactive nuclide. The decay constant in days. So the relationship that we have here is that the natural log of the activity is going to scale as the decay constant, or 1 over the decay constant. It's going to scale as 1 over the decay constant. So we have our 1 day, the activity goes down by a factor of 10 to the 6. So that's showing us that the decay constant is 6. Sorry, it'd be a lot easier if I could write this equation on the board, but we don't have it there. Particular radioactive substance emits both beta plus particles and neutrinos. What describes the nature of the energy spectrum? This is a subtlety on beta decay. And so we know that the spectrum of beta particles is actually, it's a continuous one because we have different energies for the neutrinos. Of course, if this is going to be continuous, the neutrinos must also be continuous to fill in the gaps. And finally, number 10, which of the following observed during radioactive decay experiment provides evidence for the existence of nuclear energy levels? nuclear energy levels are going to be associated with a spectrum of alpha particle energies and also the spectrum of gamma ray energies. Beta particle energies are continuous, and they do not have they don't have to do with nuclear energy levels. Okay. Now we've got to look at our written response one. So we have state how the density of the nucleus varies with the number of nucleons in the nucleus. Because the radius varies as the number of particles to the 1/3, the density is actually constant because the volume scales as to the third. So you can't compress protons and neutrons. Show that the nuclear radius of phosphorus is about 4 femtometers. That's just substituting into the equation. We have 1.2 femtometers times that 31 to the 1/3. And so we get 3.8 times 10 to the minus 15. 11C says we form the 32 phosphorus, a different isotope, when a nucleus of deuterium collides with 31 phosphorus. The radius of deuterium is 1.5 femtometers. State the maximum distance between the centers of the nuclei for which this is likely to occur. Obviously, this is a two-step process because we're going to end up with too many of these, but we can find the maximum distance between the centers by looking at what the radius of the deuterium is with your 1.2 times the 2 to the 1/3, add that to the 3.8 here, and we'll end up with about 5.3 femtometers. In 11D, it says determine the initial kinetic energy that the deuterium must have in order to produce this. So this is where we get into our Rutherford's type scattering problem. We can look at the energy required. We have a formula for that has to do with the total potential energy between the two. We have a charge of 15 for the phosphorus. We have a charge of 1 for this deuterium. And we know what the distance is that has to be between them. So substituting into the potential energy equation of KQQ over R squared, we have K times 15 E squared divided by 5.3 times 10 to the minus 15. It's only over the distance to the first power because we're looking at a potential energy. And then, of course, that has to be kinetic energy so that it can get that close. So the kinetic energy is equal to that value. It undergoes beta minus decay. Explain why the energy gained by the beta particles is not the same for every beta particle. So we have 3 particles that are carrying away energy. We have the daughter nucleus, the one that would have, in this case with beta minus decay, it's got 32 nucleons. That's going to be carrying energy because it's so massive. It will carry very little energy because it'll be moving slowly. The beta minus particle, which is an electron, is much lighter, will be carrying a lot more energy. But the neutrino will be carrying an absolute ton of energy because of how fast it's moving. When you have 3 particles, the energy and momentum conservation means that you don't have to have a specific value of kinetic energy for the 2 particles to conserve momentum as well. You can actually split that up however you like. And so the beta spectrum is continuous. And so the particle is, each particle is not going to be the same. It's not a discrete spectrum. What is meant by a decay constant? The decay constant is the probability that a nuclear decay will occur, or alternatively, it's the fraction of nuclei that decay every second or per arbitrary unit of time. And we have a radioactive decay question. So we have a pure sample of this phosphorus isotope, and the activity of the sample is 24 becquerel. After 1 week, the activity has become 17 becquerel. Calculate in inverse seconds the decay constant. That's just going to be substituting into that exponential decay equation. We have the current activity is equal to the original activity times e to the minus lambda t. And so then we can find the value of lambda with a division and a natural log. Okay, so that's our topic 12-2 mock test. This is going to be a point to pause, and if you've got any questions, you can highlight them, and we can talk about them later, next class. I am going to switch over to the topic 7-3 material, which looks at the structure of matter. This is talking about our coming back again to the turn of the 20th century, that not long after the discovery of the electron, the nucleus was discovered and probed. The discovery of protons and neutrons followed not long after. And the development of our understanding of what was going on, not just inside of an atom, but inside that there were shells and different energy levels for the electrons to exist in, led to our understanding of the nucleus, that the nucleus was also built up of particles, and that those particles also had energy levels and existed in shells and could become unstable if the balance of forces was not perfect. We've recently looked at the Rutherford Geiger-Marsden experiment, so there's not much need to go over this again at this moment. But I did want to kind of show this timeline. You may have to slow it down a little bit. 1898, the discovery of the electron. 1919, the discovery of the proton as an isolated particle. Not until 1931, the discovery of the neutron. But then the next 30 to 50 years would involve the discovery of the positron, the muon, and then all matter of different particles that were discovered. So particle discovery in the 20th century started off with the discovery of the electron and the alpha particle, but then very quickly led to a number of particles that you've probably never heard of: pions, kaons, lambda particles, muon neutrinos. The J psi meson has a fun story behind it. W and Z bosons, and ultimately recently the discovery of the top quark at Fermilab around the time when I was in high school. So lots of things have been discovered that we didn't know in 1900, and that you don't need to know in order to study chemistry. So this is all modern physics and modern particle physics. The way we now understand matter is that we have two different types of matter. There are quarks and there are leptons. And the way we understand all forces is that there are force carriers, which are also particles. The gluon, the photon you've heard about, the W and Z boson, and the Higgs boson. People are working very, very hard to find what would be known as the graviton, which would be the particle that causes the exchange of the gravitational force. This standard model is replacing what you probably know of as the model of light and matter, which is that all matter is made up of protons, neutrons, and electrons, and that forces are the strong force, the weak force, the electromagnetic force, and the gravitational force, and that these exist as fields. It's not that that isn't true, but this model is more sophisticated and allows us to understand a larger range of phenomena, including some really exotic particles that we don't see as often. It's not just that there are 12 particles. It turns out that each of these particles has an antiparticle. So we talk about there being up and anti-up quark. down and anti-down quark. And these quarks make up and down quarks make up everything that we know inside of the nucleus. So protons and neutrons are built of up and down quarks. The more exotic quarks are the second and third generations of matter, which include the charm and strange quark, and of course the anti-charm and anti-strange quark, and the top quark and the bottom quark, the anti-top and the anti-bottom. We actually knew about one lepton. It was the first particle that, the last thing is that quarks are never observed on their own. They only exist in either trios or pairs. The first actual fundamental particle that we know, the only one that carries over from our previous model, is the electron. It has an antiparticle, the positron. The electron neutrino you've heard about, and the anti-electron neutrino associated with beta decay. And then in the second and third generation of fermion matter, we have muon and tau particles, and the muon neutrino and the tau neutrino. And of course, they have antiparticles as well. You'll notice in this map that they each have properties that define them. Charge and spin are quantized values that define these. The charge of 2/3 is the same for the up charm and top, whereas the down strange and bottom have a charge of -1/3. So they have fractional charges, less than 1 electron's worth of charge. The property spin, we're not going to learn much about, but it is the same for all quarks and also all leptons. The leptons have charges of -1 for the electron, muon, and tau, and 0 for the neutrinos. When you have an antiparticle, the charge is reversed. So the anti-up, anti-charm, and anti-top quarks have -2/3 charge, and the anti-down, anti-strange, and anti-bottom quarks have +1/3 charge. The anti-electron, the positron, has a +1 charge. Of course, the anti-neutrinos have the same charge of 0. The other thing you'll notice that they have is they have a property of mass. In this case, we use the definition of mass from Einstein's E equals mc squared to define these. So you will see these written as mega electron volts divided by c squared. So that's the m is the amount of energy divided by c squared. And the most important thing to notice here is that the energies associated with up and down quark are significantly larger than the electron, which makes sense because they make up protons and neutrons, so they must be heavier. And the neutrino is extraordinarily small. While all of these values are written in mega electron volts, the neutrino is written as less than 1 electron volt. We know that they have some mass, but it's very, very, very small. When you go to the next generations of matter, the masses increase spectacularly. You go from having 2.2 mega electron volts to 1.28 giga electron volts, and ultimately 170 giga electron volts. These are much more massive particles. Similarly to the muon and tau, you go from half a mega electron volt to 100 mega electron volts to a giga electron volt for the tau. In terms of the particles that carry force, they have no mass for the gluon and the photon. The Z and W bosons do have mass. Most of them do not have a charge. The W boson does. And they have spin 1. And that's why they are known as bosons and fermions. Fermions are particles that have spin 1/2. Bosons have spin 1. Composite fermions have spin that is equal to an integer plus 1/2. Bosons are integer numbers. So kind of being familiar with the standard model and the different players is important for this unit. I think I'm going to pause here because I'm about to be interrupted by Panther Block, but I'll pick back up again soon.